This video is brought to you by mywayteaching.com.
We use the open tube manometer to measure pressure differences. Okay, it consists of a U tube containing a suitable liquid. You can see here the liquid is filled. It is of U shape. Low density liquid such as oil for measuring small pressure differences, and a high density liquid such as mercury for large pressure differences. Depending on the pressure difference, we use the oil or we use the liquid. One end of the tube is open to the atmosphere. This is the end, and the other end is connected to the system whose pressure we want to measure. So this is connected to the system. The pressure P at A is equal to pressure at point B. See, since these 2 points are considered at same level, the pressure at A is equal to pressure at B, as we just saw in the previous measurement instrument also, isn't it? So what we normally measure is the gauge pressure, that is P minus PA. So that is proportional to manometer height H. Pressure is same at the same level on both sides of the U-tube containing a fluid. For liquids, the density varies very little over a wide ranges in pressure and temperature. So we can treat it safely as a constant in this particular example, because it varies very little. We can almost neglect it for a pressure at same level. Gases, on the other hand, exhibits a large variation in densities with changes in pressure and temperature. Unlike gases, liquids are therefore largely treated as incompressible, because there is very small change in the densities with wide change in pressure and temperature when we consider liquid. But in gases, it's varies rapidly with change in pressure and temperature. So only we can say liquids uh, are more, we can treat liquids as incompressible compared to gases. Okay. So now let us study simple problem. The density of the atmosphere at sea level is given by 1.29 kg per meter cube. Okay. Assume that it does not change with altitude. Then how high would the atmosphere extend? So at the sea level, the density is 1.29. Assume that it does not change with altitude, which means the density is constant as we go higher and higher. Then how high would the atmosphere extend? That is the question. So here, to solve this problem, we use the equation, that is rho g h. So here they have given density, that is 1.29 kg per meter cube, isn't it? And we take g as 9.8 meter per second square, and we consider, we don't know the value of h, we should find it. That is what the question is, isn't it? Yes. And this is equal to the atmospheric pressure 1.01 into 10 raised to 5. This is the pressure, right? Pascal. So we can get the value of h from this equation. One 1.01 into 10 raised to 5 divided by 1.29, 9.8. So this gives the value of 7989 meter which is approximately equal to 8 kilometer. So in reality, the density of air it decreases with height. So does the value of G. The atmosphere cover extends with decreasing pressure over 100 kilometer. We should also note that the sea level atmospheric pressure is not always 760 mm of He. A drop in the He level um, by 10 mm or more is a sign of an approaching storm. If it is changes by a 10 mm, then it is a sign that a storm is going to occur. Okay. So now let us study one more problem. At a depth of 1,000 meter in an ocean, what is the absolute pressure? What is the gauge pressure? Find the force acting on the window of area 20 cross 20 centimeter of a submarine at this depth, the interior of which is maintained at sea level atmospheric pressure. The density of seawater is 1.03 into 10 raised to 3 kg per meter cube, and we should consider G as 10 meter per second. So here the question contains three parts, and before solving the question, let's see what they have given. They have given the depth of ocean, that is H is equal to 1,000 meters, isn't it? Yes, and even they have given the density of what seawater, which is 1.03 into 10 raised to 3 kg per meter cube. This is the density. So the first question is to find the absolute pressure. So we know the equation to find the absolute pressure, that is P is equal to Pa plus rho G H. So here they have given to take G as 10 meter per second square. So we know atmospheric pressure is 1.01 into 10 raised to 5 Pascal, isn't it? And rho is 1.03 into 10 raised to 3, and the value of G is 10 meter per second, and the value of H is 1,000. Okay, so if you simplify this, 1.01 into 10 raised to 5 plus 1.03 into 10 raised to 6, we get the value as 1.04. In other words, we can express it like 104.01 into 10 raised to 5 Pascal, or we can say it as 104 atmosphere, isn't it? So this is the solution for the first part of the question. Okay. So second part of the question is to find the gauge pressure. So we know that gauge pressure is nothing but excess pressure, which is given by P minus PA. That is nothing but rho GH, which we can write it as PG. So this PG is equal to, we know the value of rho, that is 1.03 into 10 raised to 3 kg per meter cube, and G is 10 and H is 1000 meter. Okay, so we will get the value as 103 into 10 raised to 5 Pascal. So in other words, we can write it in terms of atmosphere, that is 103 atmosphere, isn't it? So this is the solution for second part of the question. So coming to the third part of the question is find the force acting on the window of area 20 centimeter cross 20 centimeter of a submarine at this depth, the interior of which is maintained at sea level atmospheric pressure. Okay, the pressure outside the submarine is given by, that is P is equal to PA plus PGH. Outside the submarine is nothing but what? It is in the sea only. So we have to consider that absolute pressure, that is given by P is equal to PA plus PGH. This is the pressure outside the submarine. Okay, and pressure inside it is PA. This is the pressure inside the submarine. Isn't it? Yes. Hence, the net pressure acting on the window is nothing but gauge pressure. So the question is to find the gauge pressure now, isn't it? So the pressure outside the submarine is P is equal to PA plus rho GH. So if this is the pressure at outside the submarine, then this PA is the pressure inside the submarine, isn't it? And then the net pressure which is acting on the window is nothing but the excess pressure, or in other words, we can call it as gauge pressure. So that is given by P minus, yeah, usually we'll represent gauge pressure as P minus PA only. So which is PG, that is rho GH. Since the area of the window, they have given it as 20 centimeter, right? 20 centimeter cross 20 centimeter. If you convert it in terms of meter, then we'll get 20 into 10 raised to minus 2 meter, 20 into 10 raised to minus 2 meter. So we get it as 0.04 meters square. So the force acting on it is given by F is equal to Pg into A. So we already know Pg. In the part B, we found the value of gauge pressure, that is 103 into 10 raised to 5 Pascal, and area is 0.04 meters square. So if you simplify this, then the force acting on the window of the submarine is given by 4.12 into 10 raised to 5 Newton. So this is the solution for the third part. Okay, 4.12 into 10 raised to 5 Newton. This is the force acting on the window of area 20 cross 20 centimeter of a submarine at the depth of 1000 meters. Okay.